Yet again, one of the most unmistakable and advanced physicists has offered his viewpoint regarding this issue. Michio Kaku, recognized for his remarkable contributions to the field of physics, has recently confirmed that the James Webb Space Telescope has discovered 6 enormous galaxies that scientists thought couldn't exist. These findings have the potential to open up new dimensions in our scientific understanding of the universe. The discovery is both exciting and groundbreaking, challenging existing theories about the formation and evolution of galaxies. It is, therefore, worth paying close attention to these developments. The affirmation by such a distinguished scientist as Michio Kaku highlights the importance of these findings. Michio Kaku is an extraordinary figure in the scientific field, a physicist of American and Japanese heritage. He is considered an expert in both classical experimental physics and quantum mechanics. Unlike some of his more conservative and skeptical peers, Kaku has always been open to astonishing results, including those from the James Webb Space Telescope mission. His willingness to embrace new discoveries and share them with the public underscores his commitment to advancing our understanding of the universe. We are delighted that this distinguished scientist has chosen to break his silence and publicly share what can no longer be denied. The enthusiasm and almost playful tone of the renowned astrophysicist are evident in his remarks about the discovery made by the James Webb Space Telescope. He expressed that this finding has sparked his interest. Join us in exploring the implications of Michio Kaku's revelation of these 6 gigantic galaxies. Kaku is a scientist who has always been willing to consider new theories. Throughout his life, he has demonstrated openness to ideas that challenge the status quo, understanding that Einstein's equations of relativity and Newton's laws, while fundamental, are insufficient to capture the full complexity of the universe. Kaku recognizes that the discovery of these new galaxies has the potential to revolutionize the scientific field. Although many of his colleagues struggle to adopt this view, it is creating concern and sleepless nights among Big Bang proponents and opponents of quantum mechanics. However, this only amuses Kaku. The James Webb Space Telescope has revealed 6 massive galaxies dating back to the earliest epochs of the universe. Each of these galaxies contains more stars than our own Milky Way, despite having formed only a short time after the Big Bang. The team of astronomers who made the discovery has named these extraordinary galaxies universe breakers because, if confirmed, they would overturn our entire understanding of the cosmos. The implications of these findings are profound, suggesting that the universe's early years were far more dynamic and complex than previously thought. Something doesn't fit anymore. The Big Bang Theory tells us that the universe was a chaotic mess after the initial event. The first solid objects required billions of years to form, and it took millions more years for them to reach sufficient density and produce light. The formation of complex structures such as galaxies was thought to occur much later. Some of these newly discovered galaxies surpass the Milky Way in size, and their immense luminosity indicates they were likely forming many new stars each year, while our galaxy forms stars only sporadically. It remains unclear exactly when the first galaxies formed. Scientists have not yet determined this. The only certainty is that at first, there may have been only single stars or small clusters of stars, which eventually merged to form increasingly large conglomerates until dwarf galaxies developed. These small galaxies collided with others and gradually became larger. By past theories, highly organized and massive galaxies could not have existed at that time. This raises the question of whether the universe is much older than previously believed, or whether complex cosmic structures developed far earlier than expected. This scenario is difficult for conservative science to accept, as it still struggles with this model. Certain aspects of physics heavily resist this discovery, questioning possible errors in age estimations. Michio Kaku is aware of this and had this to say. There are many examples of old and false theories that stubbornly persisted because of the prestige of certain scientists. Many of these theories were only debunked when a critical experiment exposed their flaws. Therefore, the key work in any science, especially in physics, lies within the experimentalists who keep the theorists in check. In truth, we still know very little about the true origins of the universe. This statement from Kaku emphasizes the importance of constant experimentation and validation in the scientific process. The Big Bang Theory was established in 1927 based on observations of the universe's expansion. These data led to the conclusion that the universe began from a single point and has been expanding ever since. At the time, it was difficult for people and scientists to imagine a universe with a beginning and an end. The idea of a universe that had always existed and was infinite in space and time was beyond people's imagination. Even today, scientists struggle to comprehend this. However, it is essential to consider these possibilities. These new discoveries don't align at all with what scientists have built their assumptions on for decades regarding the Big Bang Theory. Science has repeatedly shown that reevaluation and openness to new ideas are critical parts of the scientific process. Just as the confirmation of certain theories and observations is necessary, so is the willingness to challenge established beliefs. When Einstein was a child, it was believed that the stars and planets were fixed in the universe and occupied a defined space. However, we now know that everything in the universe is in motion. Planets orbit stars. Stars move within their galaxies at hundreds of kilometers per second, and entire galaxies speed through the universe, whose fate we cannot yet predict. This dynamic understanding of the universe challenges long-held beliefs and underscores the need for ongoing inquiry and adaptation in scientific thought. Today, scientists are challenged to accept uncomfortable truths and understand that theories are not absolute facts until they are rigorously tested and confirmed by empirical observation. The idea of the Big Bang emerged from the recognition that galaxies are moving away from each other, and this distance is proportional to their separation from Earth. This observation, known as Hubble's law, suggested that the universe was expanding. For a time, phenomena like cosmic background radiation, the redshift of light from distant galaxies, and other cosmological observations seem to support this theory. However, it is important to remember that, in the past, people who believed the Earth was flat or that the sun revolved around us also had physical evidence for their assumptions, until advances in observation and technology provided clearer, more accurate pictures. Now, we find ourselves in a similar situation. Scientists expected the new James Webb Space Telescope to confirm assumptions related to the Big Bang. Instead, it has revealed these 6 galaxies that seem impossible. The James Webb Space Telescope, JWST, has brought forth a wealth of data that is reshaping our understanding of cosmic history. While many anticipated that its findings would reinforce established theories, the unexpected discovery of these universe breakers has raised fundamental questions about the timeline and processes of galaxy formation. These massive galaxies, forming so soon after the Big Bang, suggest that the early universe was far more efficient in creating and organizing matter than previously thought. If confirmed, this would require scientists to revise long-standing assumptions about the rate of star formation, the density of matter, and the interplay of forces in the universe's infancy. Such discoveries also point to the possibility that alternative models of the universe's origin may hold validity. Some theories suggest a cyclical universe, where phases of expansion and contraction occur infinitely. Others posit that the Big Bang was merely one event in a broader multiverse, with each universe possessing its own unique conditions and physical laws. Michio Kaku has often expressed openness to such radical ideas, emphasizing the importance of embracing uncertainty and remaining flexible in the face of new evidence. His willingness to challenge orthodoxy sets an example for other scientists, reminding the world that progress often stems from questioning the status quo. The implications of the JWST's findings extend beyond physics and cosmology. Philosophers and theologians have long grappled with questions about the universe's origins and humanity's place within it. These discoveries may provide fresh perspectives, encouraging interdisciplinary dialogue that bridges science, philosophy, and spirituality. Moreover, the technological achievements behind the JWST itself deserve recognition. The telescope's unprecedented resolution and sensitivity have unlocked a new era of observational astronomy. Its ability to peer deep into the past, observing light emitted billions of years ago, offers a glimpse into the universe's formative moments, revealing secrets that were once thought to be beyond our reach. As we continue to analyze the data from the JWST, the scientific community must prepare for more surprises. The discovery of these 6 massive galaxies is likely only the beginning. With each new observation, we refine our understanding of the cosmos and, by extension, our understanding of ourselves. Science, as Michio Kaku reminds us, is a never-ending journey of exploration and discovery. While it is tempting to cling to established theories and models, the history of science teaches us that true progress often requires embracing the unknown. The findings from the James Webb Space Telescope challenge us to expand our horizons, reconsider our assumptions, and dare to imagine a universe far more intricate and wondrous than we ever thought possible. In the words of Kaku, the universe is not only stranger than we imagine, but stranger than we can imagine. With tools like the JWST, humanity is beginning to grasp just how vast, mysterious, and magnificent our cosmos truly is. Should be available to new disclosures and reevaluate existing hypotheses in view of the accessible proof. The surprising finding tested the momentum understanding and provoked a reassessment of well-established cosmological speculations. Specialists utilize redshift as a tool to determine specific quantities in the investigation of the universe. Redshift, otherwise known as the Doppler effect, refers to the adjustment in the color of light as the light sources and the spectator move relative to one another. To understand this, you can imagine stopping and seeing a vehicle coming towards you. As the vehicle moves towards you, you hear the engine getting louder. However, once the vehicle passes you or moves away, the engine sound changes. This is because the engine sound varies as the vehicle moves. The same is true for light. When a light source, for example, a distant star, moves towards us, the light we see shifts towards bluer tints. On the other hand, when the light source moves away from us, the light shifts towards redder hues. This phenomenon is called redshift. Physicists have converted redshift values into speeds and distances for measurement in the investigation of the universe. However, it is vital to note that small errors in these measurements could have huge effects. The measurement techniques previously used are currently under review, and it is interesting to see what results scientists will arrive at concerning the latest demonstrations related to our universe. It is important to consider whether they are truly based on redshift errors or whether some scientists are simply denying the facts. This is a question that requires thorough examination and careful review of the data and methods used in the research. The ongoing analysis and reevaluation of measurement methods highlight the evolving nature of scientific inquiry. Thank you kindly for watching the video. As always, we remind you that you can post your questions in the comments box. If you like Michio Kaku's investigation video, remember to hit the like button, share so it reaches more people, and subscribe to the feed so you don't miss more content like this. Thanks again for watching, and see you in the next one. This call to action urges viewers to engage with the content, fostering a community of curious minds eager to explore and understand the latest scientific discoveries. The study of our universe, with its vast scales and intricate celestial bodies, continues to captivate and challenge scientists across the globe. From the early theories of the universe to the latest discoveries made possible by cutting-edge technology, each discovery reshapes our understanding of the universe and pushes the boundaries of human knowledge. One of the most profound and enduring questions in cosmology revolves around the origin and evolution of galaxies. Galaxies are enormous cities of stars, gas, dust, and dark matter bound together by gravity. Understanding how galaxies form and evolve is essential not only for unraveling the mysteries of our universe, but also for confirming or challenging existing theories, such as the Big Bang Theory. The Big Bang Theory, proposed almost a century ago, posits that the universe began from a singularly dense and hot point and has been expanding ever since. This concept arose from observations of the universe's expansion and the cosmic microwave background radiation, considered the remnants of the early universe's intense heat and light. However, recent discoveries, particularly those made by the James Webb Space Telescope, JWST, have challenged some fundamental assumptions underlying the Big Bang Theory. The JWST, with its exceptional sensitivity and resolution, has detected galaxies that defy conventional understanding. These galaxies, dating back to within a few 100 million years of the Big Bang, are unexpectedly massive and luminous, suggesting a more dynamic early universe than previously imagined. The implications of these findings are significant. They raise questions about the timeline and mechanisms of galaxy formation, prompting scientists to rethink existing models. For example, the discovery of galaxies already so developed shortly after the Big Bang challenges the notion that galaxy formation was a slow and gradual process occurring over billions of years. Additionally, JWST observations have highlighted the complexity of cosmic evolution. It is now evident that galaxies can grow rapidly and exhibit significant star formation activity early in their histories. These insights compel astrophysicists to revise their theories on how stars, gas, and dark matter interacted in the universe's infancy to form the first galaxies. Beyond revolutionizing our understanding of galaxies, these discoveries underscore the critical role of technological advancements in pushing the boundaries of astrophysical research. The JWST, with its infrared capabilities, allows scientists to peer further into space and further back in time than ever before. By studying the light emitted by distant galaxies, astronomers can reconstruct their histories and uncover clues about the conditions that prevailed during the universe's early stages. The concept of redshift, a vital tool in cosmological research, plays a crucial role in these investigations. Redshift refers to the phenomenon where light from distant celestial objects shifts toward longer wavelengths as they move away from us. This effect, known as cosmological redshift, provides valuable information about an object's distance and velocity relative to Earth. Through careful analysis of redshift data, scientists can infer the size, age, and evolutionary stage of galaxies observed by telescopes like the JWST. However, interpreting redshift measurements requires precise calibration and an understanding of potential sources of error, such as gravitational lensing and instrumental limitations. In addition to studying individual galaxies, cosmologists are also exploring larger cosmic structures, such as galaxy clusters and superclusters. These vast assemblies of galaxies are bound together by gravity and offer insights into the distribution of matter on cosmic scales. By mapping the spatial arrangement of galaxies and measuring their velocities, researchers can trace the cosmic web, a network of structure that spans across the universe and defines the large-scale architecture of galaxies. The cosmic microwave background, CMB, radiation represents another invaluable source of information for cosmologists. Discovered accidentally in 1964, the CMB is the faint glow of radiation left over from the Big Bang itself. As the universe expanded and cooled, the intense heat of the early universe diminished, leaving behind this pervasive background radiation. Detailed measurements of the CMB's temperature fluctuations provide a snapshot of the universe's infancy, revealing primordial density variations that ultimately gave rise to the galaxies and cosmic structures observed today. These density fluctuations, imprinted in the CMB, are a treasure trove of information about the universe's origins and composition. By analyzing the patterns of these fluctuations, scientists can infer key cosmological parameters, such as the universe's age, the rate of its expansion, known as the Hubble constant, and the proportions of dark matter and dark energy that dominate its content. Dark matter and dark energy remain two of the greatest mysteries in modern astrophysics. While dark matter is thought to be a form of matter that interacts gravitationally but not electromagnetically, dark energy is a hypothetical force driving the accelerated expansion of the universe. Despite their elusive nature, their combined influence shapes the structure and fate of the cosmos. The study of dark matter and dark energy has been propelled by observations of large-scale cosmic phenomena, such as galaxy rotation curves, gravitational lensing, and the distribution of galaxy clusters. These observations consistently point to the presence of unseen mass and an unknown force influencing the universe's behavior on grand scales. Moreover, the interplay between theoretical models and observational data has been central to advancing our understanding of cosmology. Theoretical physicists use mathematical frameworks, such as general relativity and quantum mechanics, to develop models that describe the universe's behavior under different conditions. Observational astronomers, in turn, test these models by gathering data from telescopes, satellites, and other instruments. The rapid development of technology, such as the James Webb Space Telescope, the Rubin Observatory, and the Square Kilometre Array, continues to revolutionize our ability to observe the universe. These instruments enable scientists to probe deeper into space, detect fainter objects, and gather data across multiple wavelengths of light. In the coming years, the synergy between observational data and theoretical models will likely lead to new breakthroughs in our understanding of the cosmos. As we refine our measurements and improve our models, we may unlock answers to long-standing questions about the universe's origins, structure, and ultimate fate. This ongoing quest for knowledge underscores the essence of science, a relentless pursuit of truth, driven by curiosity and a willingness to embrace new ideas. Each discovery adds a piece to the cosmic puzzle, bringing us closer to a comprehensive understanding of the universe and our place within it.